Welcome to our ongoing OSPF series, Huawei Routing, OSPF Routing series. When we dropped off last time, we promised to bring you a series on network types and DR/BDR election. When we looked at the last video, we covered how a neighbor transitions. The OSPF, once they form neighbor relationship, they transition from neighbor relationship to adjacency. And we said a stable neighbor relationship can be two-way or full. So once you form a neighbor, they become in two-way state. Then they'll undergo through processes that will determthen whether it will become a full neighbor. So from two-way, we looked at how we transition to ExStart, where then the routers are trying to establish the neighbor relationship, determine who is the master and who is the slave. And we say this is because we want to know who will take control of the sequence number, because the sequence numbers are used for acknowledging LSAs. And then after the ExStart, it goes through exchange, where we exchange the first database description packet. The database description is to tell the neighbors what LSAs I have in brief, not the details, but in brief. Then there is loading, whereby a neighbor will request for the missing LSAs, and then it will get an update, and then it will acknowledge using the sequence number that was set up during the ExStart. And then after that is complete is when we form a full neighbor. Then what you're saying is that not all OSPF routers will form a full adjacency. Whether it will be stuck at two-way or at full, it is determined by the network. The network type determines which routers will form full adjacencies. So that is what we are going to look at in this particular session. So what happens during the exchange? During the exchange, we said we are having the first database description, where the router will give a brief of the network components of the network LSAs that it have. It is a brief. We talked about the last video, we said it's a trailer. It's a trailer, it's not the full description of the LSA that we have. Then, what happens during the loading? What happens during the loading? During the loading is that one router, we look at the database description and see, look, I do not have the LSA for network X. So it will request from the neighbor, it will send a link state request. And then the neighbor will send the link state update. And then after the link state will update, the router that requested will send back a link state acknowledgement. So you can see loading has a couple of messages to be exchanged. And also, before that happens, we have packets to be exchanged. First packet to be exchanged is the database description. So forming an adjacency, as you can see, it's not a one-off process. It's layered. It's layered with database description, link state request, link state update, and link state acknowledgement for each neighbor relationship. We'll go through this transition for it to become full. So this is what we had in that other network, that we are demonstrating two neighbors. We are demonstrating two neighbors, OSPF neighbors, forming an adjacency, transitioning from two-way to full state, where after full state, and we are saying it is the full state is preceded by ExStart, where we are negotiating who is the master and who is the slave, and then the first database description packet that has LSA briefs. We said LSA brief, it's not a complete LSA details, it's a trailer. In the last video, we said it's a trailer. It's not the full description about that network. Then if a router finds that is missing a particular network, it will request for it. Like here, This one, router B, notices that we do not have 1.1 in our database description, so it requests for it. And then router B will send the update, the full description of that network. We looked at this in the last video, and then I'll leave the link in description. And then B will acknowledge. It will acknowledge that I've actually received that update. We looked at this, and this is only for two routers. As you're saying, one-to-one relationship, that is what will happen for the router transition from two-way state to full state. Full means adjacency has been formed. And that means if adjacency has been formed, the two routers can exchange LSAs, the link state updates. But what happens when we have more than two routers forming OSPF on the same network? What happens is that each router, for them to exchange LSA, because OSPF cannot start forwarding traffic if the whole database has not been built using the LSA from all the routers. So each router will try to establish an adjacency with every other router. So router A will establish adjacency with router B, router C, and router D. Okay, so those are three adjacencies. Then router B already has an adjacency with router A, so it will establish an adjacency with router C and router D. So those are two adjacencies. Then router C has already established adjacency with router B and router A. So it will only be remaining with router D to form an adjacency. So as you can see, we have 6 adjacencies for 4 OSPF router. And imagine what happens for each relationship. We have all these processes, all these for each relationship. For that processes will be repeated for each of these relationships. The ExStart, the exchange, and the loading, so that each can get to full state. So we are saying that one forces it to form a full mesh. And the formula for full mesh, to determine the number of relationships that we will have, is determined by this formula, n times n minus 1 divided by 2, where n is the number of routers. In this case, we have 4 OSPF routers. So 4 times 4 minus 1 is 3, divided by 2. So that becomes 4 times 3, which is 12, divided by 2. So we have 6 relationships. And for each of these relationships, we'll have ExStart, exchange, and loading before we transition to full. But now that one brings a very big problem, because it will mean each router will require to have very high processing capacity, very high memory, and sometimes take a long convergency time. So that method where we have forming full mesh determined by that formula, n times n minus 2, does not scale very well for many routers. So you can see from this diagram, when we have 3 routers, basically 3, but as we begin to increase the number of routers, the number of relationships grow exponentially. You can see we are increasing the number of relationships, which means we need very powerful routers that have very high memory, and they will consume a lot of bandwidth, and then convergency will be slow. So that is the biggest problem of having a full mesh, that each router is having a full adjacency with every other OSPF router. So how does OSPF solve this? OSPF says that not all OSPF routers in a multi-access network will form adjacencies. So it determines a couple of networks and says some types of these networks will form full adjacencies and others will not. So from a lab perspective, let's see practically how that one happens. In this case, we have a router, we have an OSPF network, that is multi-access. They have multi-access because they are using one network segment to establish an OSPF relationship. So in this case, if we look at one of the router, like router A, we look at its neighbor. This is how you look at neighbors in Huawei VRP. So you say display OSPF peer. You will see the neighbors it has. To make it readable, we can say brief. So you can see it has 3 neighbors, which is correct. This router has 3 neighbors. 1, 2, 3. Correct. It has 3 neighbors. But it only has full relationship with only 2 other neighbors. 4.4. 4.4, we'll see which one is 4.4. And then this other neighbor, it's stuck at 2-way, which means it only formed neighbor relationship, but did not transition to full, not form adjacency. So that's what we are saying in that statement, that not all routers will form full adjacencies. Some will remain at 2-way, because so as to reduce the number of adjacencies that we are having, so that we do not have that exponential increase in the number of adjacencies when we increase our router. The networks are meant to grow because data grows, network usage grows. So when network grows, you do not want to have all routers forming full adjacency, because it means you'll need to have powerful routers that are using a lot of bandwidth. And when things go wrong, they take a long time to converge. Okay? To converge. If in a multi-access network, not all OSPF routers are forming adjacencies, how do they exchange link state information? Because we said for them to start exchanging link state information, they must have full relationship, full adjacency. But I have seen from the lab, there are some routers that do not have full adjacency. Like one of them was stuck at 2-way. So in that 2-way state, how does it receive link state information, and how does it send link state information to the others? That is the biggest question. So we bring in an estate analogy. When we were moving in our estate, we used to be the two of us, me and my neighbor. So the two of us, when we have information, we would easily exchange with each other that I have learned about this estate, and the other one will say, I have learned about this from this estate. So it was easy from when we were two. And then we increased. There come a third neighbor. And now, if I learn information, I have to inform the first neighbor and the second neighbor. So three of them. 2 messages. I have to send 2 messages. And them, likewise. If they learn something, they have to inform me and the other neighbor. So you can see what is happening here. So as the neighbors increase, the amount of information I have to send, same information, I have to send it a couple of times. So you can imagine when the estate grew and we became 10 neighbors, 20 neighbors, and every information has to be sent to every other neighbor, it became a problem. So the idea was mooted that we have an estate, organization, and then in the estate organization, we elect an estate chairman. And then when we elect an estate chairman, when the neighbors come in, new neighbors come in, they will be informed by one of the neighbors that here we have a nested organization, and these are the neighbors I know, or these are the neighbors that we have, and we have a chairman. This is the chairman, this is where the chairman lives, and that is exactly how OSPF works. When a neighbor joins, they get a hello packet from an existing neighbor, and a hello packet will have information about the DR, which we'll talk about it, and the BDR. So the asset is told, the neighbor is told, we have a chairman here, and these are the neighbors that I know. Fantastic. So if you have information, you will forward the information to chairman. You will forward your information to chairman, and then chairman forwards that information to all the other neighbors. You see how it works? So this neighbor will not forward information to the number 2. He will take the information to the chairman. Then the chairman will send the neighbor information to the other neighbors. So in essence, it's only like this neighbor is forming a full relationship with the chairman only. And this neighbor is like forming a full relationship with the chairman only. Like that case when we had only 2 neighbors. And now we have many neighbors. But the most important thing is that the relationship, the adjacency, is formed between the neighbor and the chairman. Then the chairman is the only one that forms relationship with everyone else. We'll have as many relationship as the neighbors. Okay. So this is how it compares. Is that the estate is our multi-access network. The network whereby we have OSPF routers forming OSPF relationship in one network segment, but we have several of them. And then the residents are our like OSPF routers. Then the estate chairman is like our designated router. Designated router is a chairman, and in every estate there is always a deputy chairman, such that if the chairman is incapacitated for some reason, the deputy chairman takes over immediately without having to do another election, because another election, takes time, it's costly. So OSPF does this to fasten convergency, such that when things go wrong, we do not have to go back to election. We have someone on standby very fast to take over. And then the estate information is the link state information that we are exchanging. The actual information about networks that OSPF need so that they can build something called link state database, and they can start exchanging forwarding traffic based on that. And then residents announcing themselves, you send a hello packet. So you send a hello packet, and then you receive a hello packet telling you who is the designated router, who is the backup designated router, and the neighbors that I know. And then the role of the chairman is the DR's role to coordinate the information about link state information. He'll say, I have received new link state information from router A. To all these other guys, you should receive this information. So that is where the DR comes in. So neighbor to neighbor, that is not a DR, exchange of link state information is stopped, so that we can reduce the number of meshes, the number of adjacencies that we are forming. So what criteria do we use to choose our chairman, who is our DR? How do we elect our DR and our BDR? So DR, as we have said, BDR is also elected together with the DR, so that we, in case of failure, we can have fast convergency without having to go through the election process again. So routers run the election locally using OSPF hello packet. So a hello packet will have priority and router ID information. Let's look at how that one looks like. We had a packet capture here earlier. This one we did so that we can also reduce convergency. We will reduce the number of times we have to wait for something to capture. So if you look, this is a hello packet. This is a hello packet, an OSPF hello packet. Among other things, an OSPF hello packet will contain priority. You see, there is a priority, and the other thing it will contain is the router ID. Let's look at the router ID. If you look at the header, it's contained here in the header. It will tell you the router ID that is sending this packet is 4.4.4. It will contain the router ID. So it will contain those two things. Then the routers we look will start with that priority. We have said the hello packets contain the router priority. So the first criteria is to look at the priority. Who has the highest priority? And the priority is a number between 0 and 255. We have seen from our packet capture that the priority is 1. So by default, in all Huawei routers, the priority for all interfaces is 1. All OSPF interfaces, the priority is 1. Let's see that one with a practical case. We had this earlier. So we can say display OSPF interface. And you can see the priority is 1. Here is the priority. By default, the priority is 1. The priority by default is 1. And then the router with the highest priority wins the DR with the highest priority. So if you leave it at default, priority will not be used in determining the DR because all of them will have same priority of 1. And we are saying the second highest priority wins the BDR role. So you can change the priority of the interface, and we shall see why that is important later, using the OSPF DR priority command under the OSPF interface. A priority of 0 means the router cannot take part in the election. It is disqualified. If you have something like that, there's a member you know is not reliable, can never take place in any election, or does not meet criteria, we can discourage them from being considered to be a DR or BDR. So we can send those interfaces to be 0. For example, if you have a weak router in your network that you're not sure about its reliability, you can set its interfaces to 0, to a priority of 0, so that it will never take part in the DR BDR election. If there is a tie on priority, we go to the second order. The second order, remember our hello has both priority and router ID. The second order looks now at the router ID. So the OSPF router with the highest router ID wins the DR election. How do we get the router ID? The router with the highest ID wins the election. So a 3.3.3 will beat 1.1. So how do we get the router ID? If the router ID is not configured, you can use when we come to configuration, we look at that. You can look at our journey. First is to learn to understand the protocol, and then later we'll come to configuring. When we come to configuring, we'll see how we can influence the router ID using this command. So if it's not configured, router ID by default is the IP address of the OSPF interface with the highest IP. So how are adjacencies formed? Once we have our DR and BDR election, we now know who is our chairman and who is our deputy. how do we establish now adjacencies? So after the DR and the BDR election, we know our DR router and our BDR router. So the other OSPF routers that are neither DR or BDR are called DR other routers. DR other routers. And now, with that in mind, this is how we form adjacencies. DR and BDR router will form full adjacencies. Okay? And then DR and BDR routers will form full adjacencies with all DR other routers. The chairman and the deputy chairman, they will form adjacencies with all the neighbors. Full adjacencies with all the neighbors. Okay? With all the residents. But DR other routers do not form full adjacency with each other. So a DR router, a resident, and another resident who is neither a chairman or a BDR, they will not form a relationship. They only form a neighbor state, two-way. So DR other and another DR router, DR other router, they will remain at two-way state. And this is the summary. DR to BDR, DR to DR others, BDR to DR others, all of them will be full. These three will be full relationship. But DR other with another DR other, they cannot form full relationship. They will be stuck at two-way. At two-way. So let's see that from, I think here, display OSPF peer brief. So here we have been told if we display OSPF brief so that we can see who is the DR and who is the BDR. We can see the DR, the number that is used here was for 192.168.1.4. That is the router number 4, which has 4.4.4. Is a DR. And then this one, which is 3.3.3, it will be the BDR. So these two are DR. This one is a BDR, and this is the DR. And you can see here, they use the highest IP to determine who is the DR. And then we are told this router is in DR other state. So these are DR other router. So if you look at the neighbors it has with 3.3.3, which is this, is a BDR, it has a full relationship. And then with 4.4, which is a DR, this one, it's a full relationship. But 192.168.1.2, which is 2.2.2, because it's neither a BDR or a DR, it becomes two-way. It has a two-way state. It has a two-way state. So that is the lab demo. So why we should not leave things at default? We should at all time try to influence this DR-BDR election. Because one thing we note in a campus network is that our routers do not have same capabilities and roles. You always have some powerful routers in your core, and then maybe the less powerful routers at your access. So what we are saying is that if we let if you let OSPF handle the election, the least capable routers might be selected for to become the DR or the BDR, because as we have seen, OSPF does not look at the router capabilities. It only looks at priority or the router ID. It doesn't look at the router capability. So if you configured this one, the last one, the core router, the core router as the first one, and maybe you issued it the first IP that exists, and then you configured this one as the last, or this one as the last OSPF neighbor. So you went on increasing IP. So this one will be selected as a DR. You see, while this one would have preferred this one because it is more powerful. We want a chairman who is powerful, who can handle a lot of traffic because he's handling all the relationships. So we want to influence our elections by not leaving things as default. So we use priority. We can set the priority numbers. Once you set up the priority, it will ensure that that router will always become, that has the highest priority, will always become the DR. And then the second one, the one we want to be DR, we can give it a lower priority than the DR, but a higher priority than the others. So because OSPF priority doesn't actually measure CPU. It doesn't know about whether your router has higher memory. It doesn't know whether it has a higher speed or even the capability of that router. It does not understand that language. It only understands priority and router ID. So we can control that and determine which one will become our DR. So that's what we are saying in this. We are saying the engineers decide what makes a router suitable for the role. We are the one who knows that this particular router has great processing capacity, better redundancy, better connectivity, high availability, better resilience than others. So we can make it the DR by force. And the second one that has almost the same capability or slightly lower, we can make it the BDR by influencing. We can influence this election. So when we are designing, when we go back to our work, to our fields, and we should, and it's always prudent to influence the election. Don't leave it to the OSPF, because the OSPF might make the least capable router the DR, and then you'll have a slow network or a failing network. So we intentionally control the DR/BDR election. So in summary, we'll see the networks that force DR and BDR elections to happen and others that do not. So broadcast like Ethernet and FDDI will always conduct a DR/BDR election. So you should know that and influence, so that you don't leave it at default. Influence who becomes your DR and who becomes your BDR. A non-broadcast multi-access network, e.g. frame relay, LX.25, will also conduct a DR/BDR election. So careful to always know who will become our DR and who will become our BDR. And then some networks do not. Out of the 4 networks that OSPF define, the other 2 do not conduct BDR election, and this one of them is a point-to-point, point-to-multi-point. And we are saying no network is purely a point-to-multi network by default. So the common practice is to change non-full mesh NBA non-broadcast multi-access network to a point-to-point network, so that you can stop the elections here. But that's an advanced lesson. And then there is point-to-point networks do not conduct a DR/BDR election, and we're talking of point-to-point protocol, HDLC, and link access procedure balance. Those one do not conduct a BDR/BDR election. So this is a summary. I'm sorry about this. We have broadcasts will conduct, non-broadcast multi-access will conduct, point-to-point will not conduct, point-to-multi-point will not conduct an election. Will not conduct an election. So here we have a lab for you. We want you to try something practical. So assume you are a network engineer for an ISP and you have an existing aggregation network. Okay, the aggregation network from the campus setup. And then your first router that was deployed was R1, became the DR. And then the second one, R2, became the BDR. And then, because of increased traffic and more customers come in, management decides to buy a new, more powerful router with higher capacity, R4. So because R4 has a higher capacity and it's new, we are required to make it the preferred DR. So we move the DR role from R1 to R4 without restarting the OSPF process across the network. One thing you need to note is that OSPF DR election is non-preemptive. Once the elections are done, that is it. They are set on stone. That those one will be the DR and the BDR. They cannot be overthrown. The estate analogy. If the chairman was elected and a new powerful member comes in with more capability, they'll be told, oh, sorry, we did our election, we have our chairman, our deputy, until another election is done. In OSPF means, unless we restart the OSPF processes. But we are talking of a live environment, a working environment where we are not required to restart the OSPF process. So we are required to start, to influence, to overthrow the DR, the existing DR, and maybe the BDR without conducting a new election. It will be interesting to see what you will say in the comment about this. And then in the next session, we will see how we can handle that. Thank you for watching and stay tuned for the next one. Thank you.